Yeah, Assalamualaikum and good morning. So today we'll continue with our lectures. Uh, Essentially, we have more or less covered all the things that uh, regarding about Lorentz transformation previously. So today we are going to sort of move on to a sort of second part in a way of this particular course, and we'll talk about tensors. I'm pretty sure you have come across tensors at least in mathematical physics. Excuse me. But you have not. We are going to go through again because there are some peculiarities with tensors in general, relativity. Okay, because it corresponds to a different geometry from the ones that you probably have seen in mathematical physics. Okay, how many of you have done mathematical physics? Can you say yes or something? Have you done mathematical physics? Okay. Any others? I guess rest probably may have not, but in any case, we will we'll introduce tensors here, but we'll begin with scalars and vectors because these are things are known to you in high school. So and they are part of the general objects called tensors. Why we are doing this essentially because these objects tend to simplify things when it comes to describing certain kind of physics. For example, we have seen the case of electromagnetism or electrodynamics. We can't run away from using vectors, and essentially with vectors, then a lot of the formalism in electromagnetism and electrodynamics becomes. Otherwise, you have to always deal with a set of equations. For example, the Maxwell equation, you have four of them, and then if you write for each component of the so-called electric field and magnetic fields, then you have each equation is about three equations. Okay, so that means if you have four Maxwell equations, then that means that there are 12 altogether, and they all couple to each other. So this is essentially a difficulty if you start ignoring the use of vectors. And in relativity, we tend to use a much more general object called tensors. And tensors also helps a lot in writing down the equations. It makes things rather simpler than just writing out all the components. Okay, so let me begin by saying what is scalars and vectors, and in general, particularly for special relativity. So we want to introduce these objects in the context that relativity allows you to go to different frames, but you're still describing the same physics. So we want to understand this a little bit more why we do this. So we begin with the idea of a space in general. So a space normally could be could be just Rn, for example. So you have an Rn, and within Rn itself, this is no probably you can have a Euclidean geometry here, but what are the coordinates that make up Rn is really our choice. So in other words, you can set up different coordinate system. Different observers might set up different coordinate systems, and the only thing that we need is to understand this geometry very well, and essentially we know how to transform one set of coordinates to another. Okay, so in this particular case, we are thinking of the n coordinates given by x1 until xn, and this is not necessarily the Cartesian coordinates. Okay, it could be something much more general than that. Okay, so these coordinates will be transformed usually to another set chosen by another observer. So normally what would happen in this particular case, one consider, for example, let me, is there somebody coming in? Not sure how the auto admit works anymore. Okay, everyone's here. Okay. So again, one could think, for example, in Rn, you have two observers choosing different frames. So I have one observer here, then it sets up the coordinates here, your axis, and then another observer here will set up another set of coordinates here with x dash, for example. Okay, so their what you call description is essentially localized to each observer here. So in other words, one can have different local what I call descriptions, so to speak, but somehow this local description might have some overlap where they actually can understand each other. So within this overlap, there must be some kind of the ability to transform one set of coordinates to another set of coordinates. So for instance, over here, one can begin with your axis here, x1 until xn, and then one can build another set of coordinates x1 dash until xn dash, and this x1 dash will be each one of them will be functions of the old coordinates. Okay, and similarly for the other x dash below that. So this will be arbitrary functions for the old coordinates. So in order for me to simplify this, remember always the theorists tend to write a simpler equation than just an array of equations. So one normally just write, okay, x mu dash as what you call collectively describing all this x1 dash until xn dash. So x mu dash will be a function of this all x1 until xn, and if you want, you can even make that as a shortcut as well. So I will have something like this, okay, and this is just argument of a function. Okay. So if you want to make it explicit, then you just write every of these components down. Okay. So again, if you can write, usually if the space is well behaved, and then the kind of what you call transformation is actually also well behaved, then you should be able to rewrite this kind of transformation with its inverse, going from x1 dash until xn dash, okay, to the other coordinate with the undashed coordinates. Okay, so in other words, this will be an inverse of this mapping. Okay, so this is like a mapping between the dash coordinates from the undashed coordinates, and this will be the opposite. Okay, so again we treat them as functions. Okay? And in order for us to know the how to transform this, normally we need what we call Jacobian. You have seen Jacobian before, usually in the context of integrals. Over here, we think of Jacobian as the matrix of partial derivatives. Okay, so in other words, we have J mu dash nu being equals to partial x mu dash partial x nu. Okay, so in other words, if I think I've written the matrix somewhere. Yeah, so we'll go to that later on. So some notes over here is to look at what actually happens on the both sides of the equation for this Jacobian. So the way we denote the indices follows from the right hand side, okay, from the partial derivatives. So here you have mu dash. Remember our index index summation rule. We have the idea of free indices. Okay, convention. Free indices are preserved. Okay, so in other words, if I have a mu dash on top, a superscript, call it, then we will also have a mu dash on top on the other side of the equation. But now, if you look at what happens on over here, you have nu on top, but it's at the denominator. Now we interpret this since it's the denominator, your upper index at the denominator equals to the lower index on the other side. Okay. So if one have the opposite, for example, it's not shown here. If you have a lower index at the denominator, then you have an upper index at the other side of the equation. Okay. So these are rules that we try to adhere to when we do all these index notations. Okay. The other thing that one should always keep in the back of the mind why we introduce this dash indices is simply this corresponds to a new variable x dash, really. So it's a label for the variables themselves, and the components of those coordinates, okay, given by the index. So that dash is now being transferred to here in order for us to allow a neat, concise bookkeeping in a way. Generally, it will be something like this. Instead of your x dash, it's really a different symbol here, y mu, as a function of x. So really, this dash doesn't quite say that's a different kind of index. It's just the same. The only types of index that you need to be be careful in a way because of the different behavior is whether it's upper index or the lower index. We will see this perhaps when we go to tensors under special relativity. Okay, so now we are just talking about tensors in general. Okay, so that's that. So here is the Jacobian matrix. So it's a matrix of partial derivatives of some coordinate system over the other. Okay. So normally what we do is, okay, if we really want to emphasize that we want to present the matrix Jacobian itself, then we put a parenthesis. Okay. Sometimes we will always, it depends on context of how we want to describe it. Sometimes we refer even this as the matrix itself. This really is essentially the matrix elements. So just like your vectors previously, we can think of a vector with some index, a single index. Okay, but actually that is just the component of the vector. So we do the same here. Okay, and this matrix should be, if you allow inverse transformation, it should be non-singular. So what does it mean by non-singular? Then you can actually find the inverse of that matrix. Okay? And what is the inverse here? The inverse is just giving you the what you call the inverse transformation from the dash coordinates. Remember this? We had that as function of x1 dash until xn dash. Okay, so this will be the inverse of that particular matrix. Okay, the inverse Jacobian, so to speak. So you can see there again. Here you have mu on top, and then here you have nu dash at the bottom. Okay, even though it's on top, but it's at the denominator, then it translates to the nu dash at the bottom. Okay, and you can see this is the inverse Jacobian. You can see that it actually gives you the necessary property. So you multiply the two matrices together. So remember, when you multiply two matrices, there is an index for which they must be adjacent to. Okay, so here is the dummy index, for example, adjacent to each other. Okay, so over here, what does it mean by that? Remember, you have to sum this. Okay, and these are the free index here, and these are the dummy index. Okay, and you just plug in the definition of your Jacobian and the inverse Jacobian here. Here is the Jacobian and here's the inverse there. Then essentially you can see that, okay, if I do this, it's like a chain rule kind of thing. So you get to this partial derivative. Okay, and this essentially gives you, think of your x mu and x rho. Your x mu and x rho to be independent coordinates, then this will be giving you either 1 or 0. 1 when the index are the same, okay, or 0 when it's not. Okay, so this is your Kronecker delta that you had seen somewhere before. Okay, and this Kronecker delta is really the matrix elements for your identity matrix. Okay, so that is if I want to write this as a matrix, I would really write it in this way. So this, remember this, the inverse case, J inverse times J equals the identity. Okay, so the other part would be the opposite way. So this one would be J times J inverse equals the identity. And you might say that that doesn't seem to tell you well, because your indices over here is mu and rho. Your indices here is mu dash and rho dash. Again, recall this particular fact. If you get confused about the indices being different here, just remember that, okay, the dashes is just we're transferring it from the x dash to the index. So one can actually think of this instead. So your dashes are just coming from a different variable. So in reality, the index are just the same kind of index. Okay. So that's hope that doesn't cause too much of confusion. So in other words, this delta mu rho here is just the same delta mu dash rho dash over here. So this is the thing I mentioned just now. What else? Okay. Now we have not actually described the things that we wanted to see in this particular lecture, which is the scalar and vector. Well, a scalar, as you probably learn it differently in the high school, you just say it's a number kind of thing. But really what it describes is that particular quantity, that scalar thing, is something that doesn't change under change of reference frames or change of coordinates. So in other words, if you try to describe it in terms of one coordinate, so it can be a function, the scalar can be a function. So it depends. So when a scalar is a function of other coordinates, these are sometimes called scalar field, or it's here, scalar field. So that it becomes like a function that your scalar is defined on all points of the space. Okay, so that's why it's called a field. Okay, so one can describe it as a function of the axis here, or one could equally describe it in terms of your x dash coordinates. Okay, and to differentiate, this can be written as a phi dash, but the phi dash, since it's being a scalar, your phi dash must be equals to phi. Okay, so in fact, one can actually see that this should be the same when you write your x1 dash as functions, as your x1s, okay, and or the inverse kind of thing. Okay, so the idea is scalars are just looking the same irrespective of what reference frames or what coordinates that you are using. Okay. Now, when I say the same, it doesn't mean the form is the same. This we will look at this particular example over here. So I can talk about this three-dimensional space with xi being described by xyz, your Cartesian coordinates, and your xi dash is given by your spherical polar. Okay, and then I consider a scalar field, okay, which is the same form in its function, what I call in its function description. Okay, so x squared plus y squared plus z squared. So this is in the Cartesian coordinates. But if you really think of what this is in terms of spherical polar coordinates, this is r squared. Okay, so this r squared is really a function of a different set of coordinates. And this function really is, if you write it in full, it will be something like r squared sine squared theta cos squared phi plus r squared sine squared theta sine squared phi, and then r squared cos squared theta, which is really your x squared plus y squared plus z squared. And the fact that this, when you add those up and then use your trigonometric quantities, identities, then it becomes r squared. Okay. So over here is again another thing perhaps I can highlight is the fact that in some cases you find that certain coordinates might give you a better description in some sense. So in other words, over here you only need to use your r squared instead of your theta and phi somehow cancels out in this particular function. Okay, So there are some scalars where it's more convenient to write it in terms of your Cartesian coordinate, and there are some scalars for which you are, no, it's more convenient to write it in terms of spherical polar coordinates. Okay, so the choice is which one to choose is, no, it doesn't really matter, but sometimes we look at a particular problem, then you know which one is easier to handle. Okay. Okay. So the idea of this scalar is independent of the way we express it. Okay. So like this r squared and x squared plus y squared plus z squared. Okay. So I have to emphasize this. Is the fact that the scalar itself is sometimes called geometric quantity. Okay. And it captures the idea that this scalar is not really what you call, it gives you the scalars is actually the same thing irrespective of what coordinates that you choose, just like your x squared plus y squared plus z squared, that value is the same as r squared. Okay, so the choice of coordinates really is, it doesn't really matter, but what you're describing is that same thing. In other words, in this particular case, you might want to think of it as a length squared. Okay, so the idea of a length squared then would actually describe a more geometric version of the quantity itself. Okay, so the next one that you have seen is vectors. Okay, again, vectors, when you learn about this in school, you talk about being there's a magnitude and direction kind of thing, but and then when you go to probably a slightly higher, then you start to write in terms of components. Well, both of it is actually the same description, but no, one is more geometric, the other is more algebraic, they call it. So the component ones are more of an algebraic description. Okay, but when you write it in terms of components, then one has to be careful. No, which components are you referring to? Which coordinate systems? So in a way, in order for us to be what you call, describe the vector geometrically, meaning no, one should not have the vector depends on coordinates, then there must be some kind of a restriction of how the vectors behave when you change coordinate system. So we have seen this before. Okay, so in this particular case, this v mu, okay, I'm going to start calling this as covariant vectors now. Covariant vectors are what? Objects with a single index at the bottom. Okay, and under coordinate transformation, these are given by this. So this, you can see that the covariant vector uses the inverse Jacobian here. So again, no, at this point you might say, how do you know which is which? Well, in this particular case, you just look at the index over here, the free index mu dash at the bottom. So I must have mu dash at the bottom. Okay, and then one should also have, okay, how the components behave in the old coordinates. So there should be an undashed coordinate over here, and then that must be summed, so that it becomes a dummy index with the index on the in this case inverse Jacobian matrix. Okay, so I hope you get some feeling of what's going on. So here you just sort of replace this rho by this mu dash in some sense. again, the geometric character is really saying that, okay, this vector is pointing somewhere in space with some direction, and then with some, no, again, the length squared, as I mentioned earlier, is really a scalar. Okay, the vector pointing somewhere in space can look different when you use different coordinate system. Okay, so this is the thing that one has to be more careful about when you describe things in much more general way. Okay, so the object here that which is geometric, okay, it doesn't have a index here. So this we can both refer to this v mu dash, and this v can also refer to this v rho. So the geometric vector v realized in the dash coordinate system, then it has components mu dash here, and realized in the undashed coordinate system, written as v rho here. Okay, so I hope you have a feeling about what's going on. Okay. So just like the scalar we tried to describe before, we describe it through a scalar field, okay, because I make it depend on your coordinates here. One could have a much more basic scalar, phi equals to 2. Okay, but 2, of course, doesn't depend on, 2 is just a number. It doesn't depend on any particular coordinate system, so you will not, I mean, it's a perfectly, what you call, good scalar, but why I introduced this idea of the coordinates, okay, is to show that, okay, you can have something like this, that, it's the same thing, but, it depends on different coordinate system. So here I go to the idea of a scalar field. Similarly, in vectors, I could have something which is like a constant vector, okay, but that is also not quite. Well, for vectors, it's a bit more complicated because you have components, okay, and the components refers to certain directions, and directions would depend on your coordinate system. So perhaps let me just go through this example, then it's a bit easier. Okay, so let's consider, for example, a scalar field. Okay, so you have a scalar field, and then this can depend on your axis here, or this can depend on your x dash coordinates. Okay, suppose I want to consider, so the scalar field is a geometric thing. Suppose I want to make a differentiation of this scalar. So a differentiation would always refer to some coordinate system. So here, for example, the phi dx mu, okay, this x mu now depends on what coordinates you choose. Okay, so this object is now defined for all points in that particular space. This sometimes it's written in this form. Okay, phi dash mu, phi comma mu, which denotes this thing. This is just one of those old things that relativity sometimes use. There's another version of this. It's written as d mu phi. Okay, these are just symbols to represent this object. Okay, so now this thing would now be defined on all what I call points of the space. So this with the index at the bottom, just like the one we mentioned before, is a covariant vector. Okay, it's a covariant vector, and it's also a field because it depends on on where you are on that particular space. Okay, so in other words, what we have here is an example of a covariant vector field. Okay, so what is a covariant vector field? It's essentially a geometry object. Okay, for which a covariant vector is defined at each point. So you can have, for example, space, and then you define, this is a bit difficult for me to, so in other words, I have some scalars defined here. Let me write this as contour lines, for example. So this is phi equals to constant as an example. Then I have along this circle I can define some, well, actually I should be talking about a different thing, but never mind. You can define some kind of direction around the circle. Okay, not necessarily the tangent, could be a normal to the phi equals constant thing. Okay, so I should be using a different description, but never mind. The idea is that you can define vector, a covariant vector in this particular case, at each point of the space. Okay? And if one looks at how it transforms to a different coordinate system, so in a different coordinate system, I will have phi dash mu dash, okay, comma mu dash, which is really the shorthand notation for that, d phi dash dx mu dash. Okay, but phi dash is really the same as phi. Okay, so I can now use what you call, I should probably write an intermediate step here. So I can write d phi dash x nu dx nu dx mu. But remember that phi dash now being differentiated with the undashed coordinate, no, that seems odd, but remember the phi dash is the same as phi being a scalar. So I rewrite this in terms of phi over here. So you get d phi dx nu dx nu dx mu dash. Okay, so this is just a simple chain rule. But what is this? This is precisely phi, sorry, this is precisely phi comma nu. And what is this? This is j nu mu dash. Okay, which is precisely this kind of transformation law that we have defined for a covariant vector. Okay, so this is one nice example of a derivative that defines a covariant vector. Really, what this is, if you really think about it, it's just the components of, if this is done in your normal three-dimensional coordinate system, this is just a gradient of phi. And you know, gradient of phi is parallel to the normal to a surface of phi equals to constant. Okay, so that's why I mentioned about the normal here instead of the tangent. Okay, so that is a covariant vector. Now, what is another kind of vector is the contravariant vector. Okay, so here again, I'm going to use a particular case of where you have a curve, just like the circle above, you have a curve. So a curve essentially is one-dimensional because you just have, if I know how to parameterize correctly, I can write this as in terms of a single variable. And usually this is done in terms of a parameter lambda. So this might have different coordinates, x1, x2 until xn, okay, but it's parameterized by a single lambda. So that defines the curve x mu lambda. Okay. So the different kind of vector that comes into this picture is if you start differentiating along the curve, okay, with respect to the parameter lambda itself, and that corresponds to essentially the tangent vector that sort of mistakenly described for the one above. Okay, so this is essentially a tangent vector, okay? And you can see that it depends on the space, the points in the space. And the tangent vector is really what we call a contravariant vector. Okay, how do you know which is a contravariant and covariant? In this particular case, using the index notation, contravariant vector are the ones with the index on top. Okay, we contrast this with this one, which is really a scalar. Okay, the scalar is differentiated with respect to the coordinates. That's a covariant vector. Here, the coordinates are differentiated with respect to a scalar, the parameter. That gives you a contravariant vector. Okay? And how does this contravariant vector transform under different coordinate systems? So you just simply use the definition of the tangent vector over here. So you get this t mu dash being simply dx mu dash differentiated with respect to the parameter. And then if you want to transform it, what do you do? Okay, you use chain rule again. And then when you use the chain rule, this gives you the tangent vector in the undashed coordinates. Okay, but now what is this? This is essentially your Jacobian that we had defined earlier. Okay, so that tells us, okay, these objects, covariant and contravariant, are two different kind of vectors. And one in relativity, this is really a crucial point because they behave differently later on in special relativity. Okay, so the contravariant vector is the index on top, a single index on top, and the covariant vector is the single index at the bottom. And the transformation laws are both different for this contravariant vector and covariant vector. Okay, one involves the Jacobian, the other ones involve the inverse Jacobian. So, okay, so enough about scalars and vectors. So if you have problems with these ideas, just go back to vector calculus that you have learned. But the problem with vector calculus that you have learned, you are describing things, okay, the normal vector calculus that you have seen in maths method, for example, okay, they are normally referring to a Euclidean geometry. In our case, later on, we want it to be done in a different geometry called Minkowskian geometry. We have defined Minkowski space, I think, earlier when we had combined the space coordinates with the time coordinate. Okay? In Euclidean geometry, there's really no difference between the covariant and contravariant, but in Minkowski geometry, there will be difference. Okay. So the next thing that we want to do is essentially to generalize these objects. Okay. So how we generalize these objects is to consider objects with more indices. Okay. So I can have something like x mu nu, x mu nu, or even mixture of that. Okay. And of course, I can have more than two. Okay. So prototype is what we call a tensor product thing. So you just simply take two vectors, for example, here is covariant vectors, and then you put these covariant vectors together and consider all possible combinations. Okay, so here meaning you have A1, A2, A3 here, for example, in the ordinary sense. This one will be B1, B2, B3. Then you have all possible combinations of A1, B1 until A3, B3. So this object as a whole, AB, will be a tensor. Okay, so AB here is essentially a tensor formed by taking the tensor product. That's why we call it tensor, by the way. By taking the tensor product between vectors A and B. So now this object now behaves. How do you think about a tensor product? It's like defining a set of, at each point in space, it's like defining, this is talking about tensor field actually, it's like defining a set of two vectors at each point. Okay, one representing A, one representing B. And it doesn't have to be orthogonal, it could be something like this. Okay, this is A, this is B. So this pair of vectors, they can be described collectively as a tensor. Okay. Now, how does tensor behave under change of coordinates? Well, in this case, it's quite easy because you already think of it as a pair of vectors over here. Okay, so you know how each vector behave under change of coordinates. So you just multiply, in this case, by the inverse Jacobian. So you find that, okay, the vectors, the tensor that you get over here is related to the tensor in the undashed coordinates by multiplication of these two inverse Jacobian. So this is the prototype. So generally, one could have any object which has a 2 index at the bottom. Just like over here, you have 2 index at the bottom, and it transforms in the same way like this one. Then that is called a covariant tensor of rank 2. Okay, or a tensor, sometimes this is much more general, tensor of covariant rank 2, because you can have different types of rank. Similarly, over there, we have done it for the case of the tensor product of two covariant vectors. We can do the same with contravariant vectors. Okay, so you make a product of two contravariant vectors, you get an object which has two indices at the top. For example, over here, I can consider A mu at the top, B mu at the top. Okay, so these are contravariant vectors, and this correspond to some new object D mu nu. Okay, so again, this is like a prototype. Okay, a general object with index, two index at the top is called a contravariant tensor of rank 2, or tensor of contravariant rank 2. Okay, and how does it behave under change of coordinates? Okay, then again, one can go back to this problem like before. You see how this individual object change. Then you have this product of two what you call Jacobian matrices. Okay. So the final thing, hopefully I finished this thing off. The final thing that we can also have is to not only take a tensor product between two covariant vectors or two contravariant vectors. I can take a tensor product between one covariant vector and one contravariant vector. And in this particular case, I will get something like this over here. Okay, so you have one, in this case, let's call this H. I'm using H here, H mu nu. And this is called a mixed tensor. Okay. Or if you want to be more precise, this is a tensor. Oh, I think it's already written there. Tensor of contravariant rank 1, referring to this index, and covariant rank 1, referring to this index. Okay. So this is the prototype. So anything which have this index written in this way, with one on top and one at the bottom, is called a mixed tensor there. And it will behave by taking the product of one Jacobian matrix and one inverse Jacobian matrix. Okay. An example is your Kronecker delta itself. Kronecker delta is quite nice in the sense that it's a tensor of maybe I should rewrite it. Constant tensor. Okay. And this is of contravariant rank 1 and contravariant rank 2. I could actually use a different kind of thing. I can do even this, for example. We'll probably see this later on. Okay. But this will correspond to a covariant tensor of rank 2. Okay. But let's look at this Kronecker delta first. So Kronecker delta is a constant mixed tensor. And the way it behaves, it should behave like this thing. So I can write down mu dash nu dash here, just following the above law. Then I have delta rho sigma j mu dash rho j sigma nu. But you know the effect of taking a Kronecker delta. Kronecker delta will have 1 if this rho and sigma is the same and 0 elsewhere. So in other words, I could have simplified this, okay, by making sure that your rho and sigma has to be the same. Okay, so I'm using this like a substitution operation here. So in order for this to be non-zero, I will need rho equals to sigma. So in other words, this rho and this sigma should be the same. So I have j mu dash rho, j rho nu dash. But what is this? This is essentially the multiplication of Jacobian matrix with the inverse Jacobian matrix. Contracted here means it's been multiplied in the ordinary sense of matrix product. But that would actually give you this. Okay, so this, in some sense, this transformation law is actually a kind of a tautology. I don't know whether you have heard this thing before. This is just like something which is, like 2 equals to 2 kind of thing. That's a tautology. Okay. Let me just finish the last one. So generally, one can have any index, any number of index either at the top or at the bottom. So one can have an object which has m index at the top and n index at the bottom. This would be a tensor of contravariant rank m and covariant rank n if it behave under transformation of coordinates in this way. Okay, so you have this Jacobian matrices m times, and then this inverse Jacobian n times. So if it behaves in this way, then only you can call it a tensor of contravariant rank M, covariant rank N. Otherwise, it will not be a tensor. Okay, so a tensor in this case is a geometric object, just like the vector has a certain kind of direction. So over here, if it's a tensor of rank 2, then you can think of a pair of vectors collectively. Okay, so you can start to think of a much more general object which have at each point you have n vectors, and collectively, how do you define this object is a tensor. Okay, so I think I will stop there for today. Are there any questions at this stage? It's a bit no descriptive at this point. Not much calculations can be done, but that is the basis of how you want to do things in relativity, whether you do it special relativity or even general relativity. General relativity is even worse because you need to make sure everything works in a much more general coordinate transformation. For special relativity, we are limited to what we have seen earlier is something which is related by Lorentz transformation. Okay, so let me just take the attendance today. So the other thing that probably before I end, the other thing is I put up the first assignment. So the first assignment helps you to prepare for the first test. I would like to have the first test next week. This is week 4, right? Hello, everyone. Are you still there? Okay, this is week 4. So let's have the test to be on Thursday next week. So you try to do this assignment and hand it by next week on Wednesday. Okay, and I'll give you the solutions after that. Okay, everyone. Oh, okay. I've forgotten about that. Since there are only 18 of you, or that's even less than 18, I think we can do it individually. Okay. So I will set up a folder for you to send in your assignments. Okay. Any questions? It's okay for you to have the test on Thursday, right? Okay, good. So hopefully you don't have too many tests for that particular week. Okay, so I thank you and perhaps see you tomorrow. Okay.